Welcome to the course on wireless communications at Chalmers University of Technology. My name is Henk Wijmers and I'm the lecturer of this course. This course is taught in the spring semester of 2019 at Chalmers, and these lectures are provided for students attending this course. So some material may be missing from these slides as presented in these videos. This is the first lecture, in which we will describe the main properties and challenges of wireless communication systems, and in which we will also recap some mathematical tools. So wireless communication systems are characterized by frequency bands ranging from very low frequencies, around 10 kHz, to very high frequencies, around 300 GHz. In this course, we are mainly concerned with systems ranging from 300 MHz to about 10 GHz in carrier frequency. So it is important to consider that communication systems below 300 MHz or above 10 GHz are actually behaving differently from what we are describing in this course. So what makes the wireless channel special compared to the wired channel is first of all that it is a shared medium. So multiple users are accessing the channel simultaneously. This creates interference which must be handled. Secondly, users may be mobile or the environment may be changing, so this makes the channel itself time varying. This places special demands on the design, which we will cover in this course. We now look into some of the mathematics of the wireless channel. Before we do that, we recap the additive wide Gaussian noise channel. In this first equation, xk is a transmitted constellation point, wk is noise, and yk is the observation. In the wireless channel, things change a little bit. So yk is still the observation, xk is a transmitted constellation point, wk is noise, but now we have also ik, which is interference from other users, and then we have a channel, hlk, where L is the delay, so the channel here has L1 plus L2 taps, and the channel itself is time varying, so it has an index k. So if we assume that L1 and L2 are 1, we see that the channel behaves as follows. So we see the transmitted symbol xk with the channel coefficient h0k, and recall that both xk and hk can vary in time, as well as the previous symbol hk minus 1 with the channel coefficient h1k, and the next symbol hk plus 1 with channel coefficient h minus 1, k. So we observe different effects. So first of all, there is inter-symbol interference. This can also be seen as the channel being dispersive. It spreads out the signal. Secondly, the channel is time varying. So the channel coefficients, the h's, they depend on k. And finally, there could be interference from other users, which is captured mathematically by ik. In this course, we will first study the channel itself. So how does the HLK behave, and what is its impact on communication? So how does this channel affect communication quality? We will then design communication systems for both single and multiple users that are able to operate efficiently over this channel. To do this, we will need a number of mathematical tools, which we are recapping in this specific lecture. Let us first look a little bit deeper into the wireless channel. Consider this scenario with a transmitter, a receiver, and an object with three propagation paths: a line of sight path, a path reflecting off this cabinet, and a ground reflection. Now the channel seen by the receiver would look something like this. So it has three distinct paths in a delay domain. This channel will change over time. If we were to look a little bit later, we would see that the channel changes actually very, very little if the time difference is very small, so say 1 millisecond. If we look a minute later, then the channel can have changed significantly because maybe the receiver has moved. So we see that the channel changes over time, so vertically, but the channel also has variation in the delay domain. The amount of spread that the channel has, so the time between the first step and the last step of the channel, is called the delay spread. It is important that in this course we'll have two notions of time: delay and time. The channel impulse response, so the values here, this amplitudes, depend on the antenna pattern and the environment, so the specific properties of the objects. The delays here in the delay domain also depend on the environment, with typical values of the delay spread being on the order of a few hundred nanoseconds. Okay, so recall that the delay spread is the time between the first path, here the line of sight path, and the last path, say the ground reflection. The channel varies over time due to mobility of the user, and of course the mobility happens at a much slower time scale. So the time over which the channel is roughly the same is called the coherence time, and this can be of the order of 10 milliseconds. So note that there are many orders of magnitude difference between the delay spread and the coherence time. As we will see in the next lecture, the channel can be captured approximately into three components: path loss, which is the decay of the power with distance, shadowing due to large objects, and multipath due to small changes in the environment. Mathematically, we can write the real passband signal as a superposition of different paths, so here k paths, each with an amplitude that can vary over time because of mobility, and a delay that can also vary over time. So the delay is represented as tau kt. In a complex baseband, we then need to take into account the carrier frequency, so then the channel becomes as written here. So we can see that the AK and the exponential combined provides a complex number which can change very rapidly in time, because a small change in delay multiplied with a very high carrier frequency results in a high rotation. So we see that we have different components that vary over time: the amplitude, the frequency, and the delay of each of the paths. In this slide, we review some of the basic concepts related to baseband and passband signals. So here on the left-hand side, we see a complex passband signal with a real and imaginary part. For instance, a modulated waveform where AK are complex symbols, say from a 16-QAM constellation. P is a pulse shape, T is time, and here big T is the symbol time, so or the pulse duration. So we see that we're sending a train of pulses, each with its own symbol AK. So this kind of signal would go through a channel, say C of T. There's a convolution operation here happening, plus noise, and then this would be the received complex baseband signal. Of course, we don't really send complex signals, we send real signals. So this is represented here in passband. So the real passband signal is the real part of the complex baseband signal upconverted with the carrier frequency. And if you were to visualize it, would look something like this. Okay, so we see that the real part has a non-zero value, while the imaginary part is of course zero because of the real operator. The received passband signal is written here on the bottom, is a transmitted passband signal with the corresponding passband channel plus noise. And we can of course relate the received baseband and the passband signal through the following equation. So what happens here in the real operator is the complex baseband signal, the complex channel, and the carrier frequency. We will also have a lot of notions in the dB domain, so we recall that a number in dB domain is 10 log 10 of that number, where x is typically dimensionless. When x has a unit, then we need to normalize with respect to some value. So for instance, if x is in watt, then we can express x in dBm by taking 10 log 10 x divided by 1 milliwatt. We recall the relation between power and energy. So power is expressed in watt, while energy is power times time and is expressed in joule. So watts times seconds is joule. We will also often use the Fourier transform. So we see that the Fourier transform of a signal is the signal multiplied by an exponential and integrated over all time. Given the Fourier transform, we can go back to the signal by doing another transformation and note the difference in change, in a sign. Some specific cases here are a delta impulse. So a delta impulse in the time domain relates to something flat in the frequency domain. A box in the time domain will result to a sinc function in the frequency domain. In general, a signal that is narrow in the time domain will be broad in the frequency domain and vice versa. In the previous slide, we mentioned the convolution operation, so here we will describe this in more detail. We have an input signal u of t, a channel c of tau, and an output signal y of t. So here is a convolution operation in the time domain. When we take the Fourier transform of every part here, so of y of t becomes y of f, then y of f is just simply given by the product of the Fourier transform of the input signal and the channel. When the channel is time varying, then things become a little bit more difficult. So here we have a channel C of tau at different time instances, t1, t2, and t3. And we see that the channel does not remain the same for all times. So we don't have C of tau, we have a channel C that depends on t and tau. And when an input signal goes through this, then at different times it will see different channels. So the figure here on the right shows the frequency transform of a channel. And we see that the frequency transform of a channel in this case is constant. When the channel changes over time, then the frequency transform of the channel will also change over time. So mathematically, we have that the channel becomes now C of tau and t, so has a delay and a time component. We can no longer have the simple Fourier relationship because C depends also on t. So in fact, we can have a time varying Fourier transform C of f and t, which is the Fourier transform of C of tau and t with respect to tau. We now recall some basic concept from probability. So when we have a real random variable, we can associate with this a probability density function if the variable is continuous, or a probability mass function when the variable is discrete. The mean and variance of this random variable are given here. So the mean is also written as expectation of x, is the integral of x with respect to the density. The variance is the expectation of x minus the mean. So it tells you how much the variable is spread out around the mean. Specific interesting kind of random variable is the complex Gaussian random variable, or the circular symmetric Gaussian random variable, denoted by z, which comprises a real part x and an imaginary part y. X and y are independent random variables with different means but the same variance, sigma squared over 2. And then in this case we can write z as being complex Gaussian, so Cn with mean mu given by the real plus j times the imaginary part of the x and y means, and variance sigma squared, which is the sum of the two variances of the real and imaginary part. With complex Gaussians, or with real Gaussians at least, we can also associate the Q function, which is the tail of the Gaussian distribution. So for instance, when x has a Gaussian distribution with mean mu and variance sigma, the probability that x is above some threshold is given by this Q function here. And this is very relevant for error analysis. A specific kind of random processes that we will use are wide-stand stationary random processes. So these are random variables that change over time, but for which the mean and the autocorrelation function are constant. So the mean of a wide-stand stationary random process is the expectation of x of t, and because this process is wide-stand stationary, this is a value that does not depend on t and is written as mu of x. The autocorrelation function of a random process is found by taking x of t multiplied by x of t a little bit later, so x of t plus tau, taking the expectation, and because the process is wide-stand stationary, this expectation does not depend on t and is then given by ax of tau. So this tells you to what extent is the random variable at a certain time correlated with the random variable a little time later, so tau later. Ax of tau depends only on tau and not of t, so we can take a Fourier transform of this guy, and this leads to something called the power spectral density function, PSD. A specific kind of processes that we will work with are additive white Gaussian noise processes, for which the mean is 0, and the autocorrelation function is a delta impulse multiplied by the power n0 over 2. We know that for a delta impulse, the Fourier transform is a constant, so the power spectral density for additive white Gaussian noise is constant. Here we review some basics of communication. So when we're sending discrete time signals over additive white Gaussian noise channel, so suppose we send symbols every t seconds, then we can write this mathematically as a symbol S of k from some constellation with some energy plus noise. When we write the energy outside of the constellation point, typically we assume that the constellation is unit energy. We then have different notions of SNR. So we have the symbol energy ES times the noise power spectral density. We call this the SNR per symbol. Now, since a symbol may comprise multiple bits, so for instance, if you use 16 QAM, each symbol actually has 4 bits. We can also write the SNR per bit as the symbol energy divided by the noise spectral density divided by the number of bits per symbol. Okay, and we call this EB over N0 or the SNR per bit. So these are different values when the symbols carry more than 1 bit. A typical task of a receiver is to recover S from R, and the way that you will usually do this is using maximum likelihood. So we take the likelihood function P of Rk given S, in which case Rk is the observation, so it's something that we know, and S are all possible constellation points. We then take the argmax, and that gives us our decision S hat K. The performance of the communication depends not only on the SNR, but also on the specific modulation format that we use. So when we use a constellation with 4 points or 8 points, the performance will be different. It also depends on how bits are mapped to the constellation. So in this 8PSK constellation, we can map bits to symbols in many different ways, and they will all have different bit error rate performance, but the same symbol error rate performance. So in this figure here, we show as a function of the EB over N0, so this SNR per bit, the error probability, the symbol error probability for different constellations. So for QPSK, which has 4 points, 16 QAM and 16 PSK. And we see that to reach a certain bit error rate, different constellations require different SNRs. So for instance, 16 PSK requires much more SNR than QPSK. Of course, with 16 PSK we can send 4 bits per symbol, and in QPSK we can only send 2 bits per symbol. Another tool that will be used is convex optimization, which I just explained here very briefly. So in optimization, you typically have a problem of this form. You want to minimize some objective function subject to some constraint. So an objective function could be to minimize the transmission power subject to constraints, for instance, that the total power is less than some threshold and some requirement on the rate, for instance. To solve this kind of optimization problem, what you would do is you would formulate something called the Lagrangian, which depends on x, and also something here, Lagrange multipliers. The Lagrangian is given by the objective function, and then the Lagrangian multipliers multiplied by the constraint, so lambda times g, and mu times h. We then find stationary points of this Lagrangian by taking partial derivatives with respect to x and also the Lagrange multipliers. Setting these derivatives to 0 gives us a set of equations, and we can then solve for x, lambda, and mu. In some cases you can find an analytical solution, but in many cases you need to do some numerical solving. So for most problems, this will give you a stationary point, which can be a saddle point. It can also be a local optimum. When the problem is convex, so that means that f is a convex function, so it's shaped like a bowl, g is convex and h is linear, then this procedure will lead to the optimal solution. There's only one global optimum, and this procedure will find it. Another important resource is the matrix cookbook for anything related to vectors and matrices. So I highly recommend that you download this cookbook, because I think you can use it no matter what you do after this course. And some important methods that we use from this cookbook are the singular value decomposition and Fourier transforms. So we recall the singular value decomposition of a matrix X, which you find in MATLAB through the SVD command. And this results in a product of 3 matrices, U, S, and V. Here S is a non-negative diagonal matrix, okay, so it has a very nice structure, easy to invert. And U and V are so-called unitary matrices. So these are like rotations in a very high dimensional space. Okay, and they have the following property, that if you take the matrix and you multiply with its Hermitian, you find the identity matrix. So you basically rotate back. So these are also very easy matrices to work with. So the SVD is a nice way to represent matrices if you want to do the manipulations with them later on. We will also use Fourier transforms. So when we have a vector B, we can apply an FFT. This is the discrete Fourier transform implemented to the fast Fourier transform, which results in a vector A. Okay, and we can actually go back from A to B by applying the inverse Fourier transform. So in this lecture, we've seen some of the main properties and challenges of wireless communication systems. In the next lecture, we will talk more about the wireless channel.